To continue, so we were discussing the solving regression problem using machine learning model with case study. Then I took us through the usual modeling iterative process, the iterative process of ML modeling. Whereby you get your data ready, put in your data, do the modeling, and then once you are done with the modeling, take the performance measure. You may have to go back and do hyperparameter optimization until you get the best value. However, that particular algorithm may not work for you. You may have to go back and change the algorithm altogether, use another algorithm, because there's no algorithm that is always better in your case. We always work on the principle let the data speak. So you can the data, which of these algorithms can get it for us easily. That's why we have to keep trying different algorithms. And sometimes we might, to improve the performance, we might have to go back to feature engineering, manipulating the feature. Sometimes we might have to go back to data preparation. Maybe the data is not good. It's so dirty. It has so many noise, so much noise there that we have to try to find a way of cleaning the data. So we took ourselves through that. Another very unique difference between classification and regression is the fact that you have to define the performance measure, the performance evaluation metrics to be used. And I told us that the best way is to go to literature, go to established literature in the area of application you are solving, and try to use the system, use the provided regression performance measure. And if you are working on an area where you are the first one to work in this area, then go ahead and come up with some of the very popular and unique ones like correlation coefficient. Try to use correlation coefficient, and then the root mean coefficient, which I've explained. So it actually try to find the error between the actual value and the predicted value. Actual value, predicted value. We squared it to eliminate the negative. In case there is negative, maybe this one is bigger than this. So that you can then add together, then square root will eliminate the effect of that square, according to mathematician. So once you are done with that, then you can be able to assess the performance of your modeling outcome. And there are also other performance measures like mean absolute error, mean squared error, mean percentage error, mean percentage error. This is the one I've described, the root mean square error. We have the coefficient of determination. And another very important one I do recommend for people to use in evaluating the performance of their regression modeling is to actually see how can you show the difference between the actual value and the model estimate. The actual value that you know and the expected, the predicted value. You can put it in a table. You can put it in a table if it's not much. Have a table tell us this is the actual value given and this is the predicted value. Maybe it's 0.2 here, 0.25. You are able to predict 0.23. This one is 2.67. You are able to predict like 2.45. So let's see how far are you away from the actual prediction that is expected of your model. And sometimes you can transfer this table into figures and plots. Make a very nice plot whereby, I think that was where we have before, make a nice plot. These are the actual value. You see, that has been provided. Your own predicted value, how close is it? This is your own predicted value. Are they closer together or are they on point? You can use different legends, different color to differentiate between the actual and the predicted. And I think I have an example for us here. Look at this example. See, after the modeling, you can see this is the experimental value. This is the experimental value in black. These are the estimated value using the developed support vector machine-based model. You can see that the expected value is like superimposing itself on the estimated value is superimposing itself on the actual value given. Experimental value means the value that we are gotten from the laboratory, which is the one that we want to compare our estimation with. You can see that they are on point. Try to plot this kind of figure to support your regression modeling. You see, you can see here, they are all falling on. Here you can see this one is falling on top of it, falling on top of it. A little different. They are not far away from each other. This is the experimental. The closer they are, the better. The best is for all of them to be on top of each other. It means the values are almost the same. It means your model is predicting excellently well. So sometimes also you can use predictive, you can use line plot, you can use this kind of plot, just estimate how well your model is modeling. This is very important. Those are some of the things you look out for when you do modeling, regression modeling. Now let us look at the case. Of course, you can always go back and do your improvement over what you are getting. No, they are still far away from each other. You want them to be closer. Then do more of optimization of your hyperparameters. Now, from practical point of view, now let's look at demonstrating WEKA as usual. You go to Explorer. So go to Explorer, and then you can open the data set. We are going to use, I'm not mistaken, let's use permeability data set. I open the data here, data set. Yeah, first of all, remember, I can't see data set inside. So remember to change it to CSV file. Otherwise, you will not locate your data. CSV, I'm looking for CSV. So let's see this permeability data. It's a regression problem. You can see. So these are the features. You click each of the features, you see the visualization. So it has depth and all those type of inputs. Permeability is what we want to predict. This is an application in oil and gas. We want to be able to predict the permeability of oil wells before they are drilled, to avoid wasting money on oil wells that may not function. So this is the output. I told you we should put the output at the last column. So let me check. Let me check it first. We can see the data set. This is the data set in Excel. Put your data in Excel. It's always good. Put your data in Excel. This is the depth. These are the inputs. And this is the output. So let your output be at the last column. It's always good. Otherwise, if it's not there, no problem. You have to get to WEKA and change it. You see, you go to classify, then you can see here, the last one in the column is identified as what you want to predict. If it is not so, I have to update it. Maybe I want to predict that. Now I want to predict ROB. Then I have to select what I want to predict. Once we put it at the last column, it automatically detects it as the one to be predicted. It's very important. So because if you forget to set the correct target to be predicted, then you end up wasting time predicting what you are not actually supposed to predict. Let's pay attention to that. So once the data is in, we are ready to go. You can check here and see the characteristics of those data, the maximum, the minimum, the standard deviation, which are very important information, statistical information about your data that you have to provide in your reports. So now we're going to classify with special reference to public machine. To get support with machine here, you go to function, in the WEKA function. We have the SMOREG. We also have the live SVM. These are both SVM. When you put it, it will tell you this is the library, LIB SVM library, where this is also SMOREG. The difference between the two implementations, there are two implementations that are a little bit different from each other. Here you have very few hyperparameter optimization to do. Here you have many hyperparameter optimization to do. It's up to you. Sometimes if you get limited results, you might have to check out the one with more hyperparameter optimization. Let's go for SMOREG. It's selected already. And then I told us once I'm in, you select how you want the data to be divided. Do you want to use cross-validation or I want to use percentage split? Let us use percentage split, 70% for training and 20% for testing. So This you click inside here, it bring out the parameters. In this parameter, batch size, debug, number of decimal places, these are all parameters, but two of them are hyperparameters. C is hyperparameter. N is hyperparameter. The difference between ordinary parameter and hyperparameter is the fact that hyperparameter affect the performance of the algorithm, whereas the parameters are just for cosmetics. It doesn't affect the algorithm result. For example, I want the number of decimal places to be 3 or 4 or 5. This is a non-issue. It has nothing to do with the algorithm. We are just passing the parameter, the back end, to be able to get our result in 2 decimal places or 3 decimal places. However, for C and kernel, they affect the upper parameter serious. They affect the model seriously. So we have to pay attention to them. The default value is polynomial kernel, and the number of C is 1. The most important upper parameter is kernel. You have to first of all optimize it before you move to C. So let's keep C at 1 and kernel at the polynomial kernel, which is the default value. So we can run the experiment. To run it, you can see now the result is out. The correlation coefficient is 0.67, which is like 67.7%. Then you have the root mean squared error. I told you is very important. There are mean absolute error. WEKA tells you order. So you have to depend on the area you are actually working. And you can actually add more. You see, more options. You can ask WEKA to add more output for you. I want the output of the entropy evaluation measure. I want to see the output of the training split, because usually WEKA will give you the output of the testing split only, the 30% for testing. The training set is not displayed. If you want it, you check it here to give it to you. Give me the error plot. See, I want to see the error plot. You can let it show for you. Cost-sensitive evaluation and also other things you want. The prediction, I want to see the prediction value, because here the prediction is not given. It only tells you the characteristics of the model you have built. You are using SMO reg, and then it tells you the input. And then if you want to see the actual predicted value, you go to more options. And here you can select how you want it. Null means don't show me. You select how you want to see. I want to see it as plain text. You can also want to put it in an Excel file directly, CSV file. You select it, but let's see in plain text. So you do it again. This time around, you can see a difference. It's showing me this is the instance number 1. This is the actual value that we were given in the file. This is the predicted value. This is the error. The difference between this and this. You can see. See? So you can take this one now, you can export it to Excel. Just select and copy and put it in your Excel, and then you can plot it to see the difference between them. You can see that we are still having negative prediction. So it means our model still needs to have more optimization. So you go in there, let's change polynomial kernel, then let's use RBF. I run it, I still keep the C constant at 1. See, it has improved from 67 to 70%. You can see the output. We see how to negative prediction. So I keep trying it. I change. Let's say I want to use maybe polynomial kernel, maybe PUK. Sometimes some function may not work, depends. You can see PUK has taken it to 99%. This is the power of hyperparameter optimization. You see, we are getting 99%. Note that we are yet to touch C. We are just playing with the kernel function only. So PUK is already giving us 99%. And you can see the root mean square error has reduced from 70 to 6.17. That is the error between the predicted and the actual. So you can see it here, 99% accuracy and 99% correlation coefficient, and root mean error has gone down to 6 point something. So we still have opportunities. You can see the actual predicted, the differences, You can see they're getting closer to each other. This is 152.067. The predicted value is 153.507. You can see how close the prediction is. You can see it, 6.something, 4.something, which is why I said sometimes you might need to put the result in a table so that people can see physically how close your prediction is to the actual expected value. And you can also see you can also indicate the error in your table. So if you are not done, you have to keep doing, check for other hyperparameter and see if you can improve it. If it cannot improve anymore, then we come back to PUK that gave us the best, and then we can now start changing the C. One, let's put it at 100. Maybe we can get improvement. C is 100. We are keeping the PUK for now, but we have not done with others. You can see that changing the C from 1 to 100 has reduced it further from 7 to 5.4. It has reduced the error. So it means prediction kept getting better. Look at this prediction: 6.8, 6.4, 0.9, 16. So you see the prediction will be getting better as you improve upon the hyperparameter. So we keep changing. Maybe let me use 1,000. And increase, hopefully you get better result. You can see here, is it increasing or reducing? You have to check the hyperparameter. It will keep increasing, it will get to a point that the performance will start going down. At that point, you have to stop and check for the other hyperparameter. So this is how you can model regression problem using support vector machine. We are using the SMOREG, which I said is very simple. You only have to optimize two hyperparameters, C and the kernel only. This is the two things. So if you decide to go in the way of lab SVM, so I've selected it in the other support vector machine, you can see we have several parameters. Among these several parameters, the first thing here you can see is classification. You have to check, you have to select here, I want to use regression. You can see I want to use epsilon-based regression, or you want to use new FVR. In that case, you are going to select the cost. C, this is the C, the cost. Then you are going to also, you have the epsilon, you have gamma, these are the hyperparameter you have to optimize. Kernel function. You see, you have to be changing the hyperparameter kernel function from polynomial, radial, sigmoidal, and the like. So that's why I do recommend, if you are starting, you go for the simple one, the SMOREG. It has very few number of hyperparameters to check. If you get your result excellently well, that's okay. But if you are not able to get what you need, then you might have to use the more sophisticated support vector machine implementation, where you have the access to several hyperparameters to be optimized, as the case may be. So this is how you model a regression problem using support vector in the environment, and then you take your performance measure, you use plot to indicate them, at least run more than one algorithm. If one algorithm is working, it's expected that you try at least two algorithms so that you can compare them. Or you compare the one with people who work on this problem before. Sometimes someone already worked on it. The maximum they got was maybe 80% correlation coefficient. In that case, you have the opportunity to increase it better, to make it better than they. You can compare your work with their own work, and then do the necessary plotting, show the result, and see if you can make it better. If things get worse, maybe you might need to build an ensemble model for the system. I hope that is very much clear.